Hello there, children. I think we need to talk about what we call the dark current. We talked about it in class and it led to consternation, and I understand why. I also know this because I'm a psychologist, and even when teaching through a webcam, I know what you're thinking. So I understand the confusion, because if this is the first time you're confronted with something like this, it can be a bit of a shock. Now the good news is, it's not as complicated as it may seem. It just consists of a couple of steps. And when you study regional neuroscience like this, like neuroscience sort of limited to very specific parts of your central nervous system, then the only way to really do it, to really understand that, is to build up a story in your brain, step by step by step. And that's what we're going to be doing today. So we're talking about the first part of phototransduction. Remember, photons come into the eye, light comes into the eye, and you need to somehow transfer that light into a signal that your brain can work with. And the first step of that happens in the photoreceptors. Now those photoreceptors are built in a very specific way for a reason. Photons kind of scatter a bit upon entering the eye, because think about it, they get refracted by the cornea, then the aqueous fluid, or the aqueous humor, I should say, sorry, then the lens, and then the vitreous humor. And then they hit the retina. And yeah, the light is focused, but those photons, they just get scattered a bit because of every time they get refracted, right? Every time something happens to them, as they're in that process of entering the eyeball. Now, it would be really nice if your photoreceptors had a lot of surface space for those photons to bind to. And that's exactly what your photoreceptors have. So remember, photoreceptors, rods and cones. Today I'll talk about rods, but the principle in cones is very similar. You have three kinds of cones depending on what type of photopigment they have, but that is a concern for a later date when we talk about color vision. For now, let's just talk about rods, because again, the principle is similar in rods and cones, and you only have one type of rod. There's only one type of photopigment in the rods, and it's called rhodopsin. So that's much easier, I think, to comprehend. Okay, now I'm going to use my fascinating pointing device, which I have constructed not 5 minutes ago. This is a rod that I drew as well as I could, and as you can see, I'm a fantastic artist, so I have to work with what I got. Rod has a cell nucleus, right? But interestingly enough, it has an inner segment and an outer segment. Now, to make things entirely clear for your neuroanatomical view on this, the outer segment is embedded in the retinal pigment epithelium. So in other words, the base of the retina. So that's here. That information kind of, you could say, flows up. And this area is where the bipolar cells connect, which in turn connect to the ganglion cells. But we're not really going to get into that a whole lot today. So remember, this is the base. This is the base of the retina. Now what you will see is that in this outer segment are all these things. And this is exactly what has happened for your photoreceptors to increase, maximize the surface space they have, so that photons can bind to as many locations as possible. And if you were to look inside this outer segment, you would see all these things, and these things are called discs. And typically the analogy is that of a stack of pancakes. If you ask me, it looks a little bit more like a stack of pizzas, because these discs are a little thicker around the edges than they are in the center. That's why you see those thickened bits at the end. Okay? Anyway, stack of pancakes. Sure. Now if I were to zoom in on this part, so you have a little bit of the disc, and you have the bulging and the thicker edge a bit, you would see something like this. Okay? Just a cut through the side. Now there's a couple of things that are very interesting. So here we have the actual disc, right? The whole thing is a disc, not just the round thing. Each pancake called a disc. And here you have three. In reality it's way more, but this is just a schematic drawing. You have three photopigments. There they are, and they're labeled R because this is a rod, and the photopigment found in rods is called rhodopsin, R. Okay. You also see that this area, this is outside the disc, but it is therefore inside the outer segment. I'm talking about this space, right? You see that there are ion channels in there. Now, if you've taken brain and behavior, then you know all about ion channels. But if you've not taken brain and behavior, an ion channel is just that. It's a channel in a cell that allows ions to pass in and out. What's an ion? Glad you asked. An ion is a charged, must be charged, chemical. Let's call it that. It's that simple. Okay? Positive charge, negative charge. Today we concern ourselves with an ion that happens to have a positive charge, and it is called sodium. Na+. You see it there. Na+. Now, that's the build-up. Okay? These sodium ion channels are not in the discs. These are in the wall of the outer segment. Okay? Now, if we zoom in even more, we're getting there. You get a picture like this. So what do we have here? Here we have, I've just put these lines in just to give a bit of an idea of a space. This is the space inside the outer segment. This again is a disc, and studded in the disc are the photopigments. You also see again, enlarged now, the sodium ion channels. Sodium, sodium, sodium. And these sodium ion channels are built in such a way that sodium, which is quite abundant outside these the photoreceptors, it likes to flow in. Okay, sodium likes to flow in. Now, if you think back to the horrors of the action potential, then you may see where this is going. When a lot of sodium enters a neuron, and a photoreceptor is a modified neuron, you get action potentials. Remember? Sodium rushes in, potassium rushes out. Getting somewhere. Now, I would like to talk to you first about the situation in darkness. No light. Okay? Your eyes are open, but it's dark. Or for that matter, your eyes are closed and it's dark. But in any case, it's dark. Now what happens then? I have drawn here very poorly, and all biochemists and organic chemists will have to forgive me here, but one part of the rhodopsin, the photopigment, is called retinal. The other part of the photopigment is called opsin. Opsin is a protein. Retinal is something else. And if you want to split hairs, retinal, short for retinaldehyde, okay, is an aldehyde form of vitamin A. What's an aldehyde? Let's not go there. Removing something, oxygen and carbon rings and things, and you don't have to know that. But when you were told as a kid to finish your carrots, this is why. Carrots are orange because they contain beta-carotene, and beta-carotene is actually a provitamin. So your body makes like vitamin A out of beta-carotene. So yes, given that retinal, is the black thing you see there, is a form of vitamin A, I think that's the only thing you need to remember. Don't worry about aldehyde forms and that stuff, doesn't matter. It's a form of vitamin A, and therefore carrots actually are good for your eyes. But anyway, in darkness, that retinal, and for the record, I call it retinal for two reasons. One is that it's a short version, as I said, of retinaldehyde, but secondly, anything on the retina will get the adjective retinol. So to make sure that we don't confuse the two, I will say retinol on the retina and retinal for this specific chemical. Okay, in darkness, the retinal is in what we call the 11-cis form, and that means it's bent. Okay, so there's a little curve in it. I've drawn this very poorly, but you can sort of see the curve here. Okay, that curved form of retinal is called 11 cis, because if you want to get really technical, it bends at the 11th carbon atom. Carbon C11, 11 cis, right? Anyway, I won't ask you that on the test. 11 cis is bent, a bent form of retinal. That's one part of the situation in darkness. Now remember, in darkness there are no photons coming into the eye, right? Because it's darkness. The second thing that's important to remember, and that's the only other step in this, okay, is that in darkness you have these green little chemicals attached to these sodium ion channels in the outer wall of the outer segment. Those green little chemicals, they're not actually green, I've just made them green, are cyclic guanosine monophosphate, cGMP. If you remember cGMP, I'm a happy man. What do? Well, in darkness they're bound to those sodium channels and they keep them open. And this is really weird and counterintuitive, because this means that in darkness, when your eyes are not stimulated by light, sodium continuously flows in because the cyclic GMP is keeping the sodium channels open, and sodium, as you can see here, just happily flows into the photoreceptor, the rod. Now what's the result of that? The result is that this photoreceptor is continuously depolarized. Remember, when a neuron, when it depolarizes, it fires an action potential? Well, it is something like that. So, as long as you're in darkness, this cell remains depolarized, and then you get to this part, which I've drawn up here. This part of the rod is just basically zoomed in on this part, so this is where the rod connects to a bipolar cell, right? To the dendrites, the receiving ends of a bipolar cell. And in that situation, because the rod is continuously depolarized, it releases neurotransmitter all the time onto the bipolar cell. So in other words, in darkness, there is a lot of neurotransmission. What neurotransmitter? Glutamate. Weird, right? That in darkness, photoreceptors fire continuously and release glutamate continuously. But you will see throughout the course that vision, as most senses really, vision is a matter of detecting differences. Now, what happens in light? Because that's really interesting, right? It's the interesting part. We're not in darkness all day. Well, then things get fascinating. Because in light, right? Light hits the eye, enters the eye, cornea, aqueous humor, lens, vitreous humor, boom, onto the photoreceptors. What happens to those photons? Remember, photon, right? I'm just going to say that's a photon. This is the dinkiest marker in the world. Those photons, they bind to what? To the photopigments. Okay? And when a photon binds to a photopigment, something happens. An interesting cascade of events. And I think this is where people got really confused. So we're going to take it step by step. 1. Light hits the eye, gets refracted 4 times, hits the photopigments, the rhodopsin, remember? In this case, because we're talking about a rod. Now, when that happens, all kinds of things go down. Because the retinal that, remember, was in the bent 11 cis form now straightens out. and it gets a different form. We call that different, straightened out form, all trans. Just a name, all trans. 11 cis, all trans, done. Okay? When that happens, if you really love neuroscience, okay, but then I'll make it simpler. But just for those of you who really find this interesting, photopigments work like a G protein coupled receptor. If you've taken brain and behavior, you know what I'm talking about. G protein coupled receptor. Some sort of chemical binds to that type of receptor, and then that receptor will release G proteins. Okay, that was the hard version of this. The simpler version of this is something like this. I'm going to simplify. There's a few more steps, but for this course I want to keep it as simple as I can. When the change occurs here, right? These retinal molecules are now straightened out, right? That's a really weird carbon. Sorry. You get the point, I hope. When they get straightened down to the all trans form, chemical processes are set in motion. But what's very important to remember is that enzymes are released as a result of those processes. So remember, when retinal goes from 11 cis to all trans, enzymes get released. What are enzymes? They're chemicals that can do things. Okay? And what do those things do, those specific enzymes? They break down the cyclic guanosine monophosphate. Now, if you reason this through, you should see where this is going. Because what did the cGMP do? It kept sodium channels open, so sodium could enter the photoreceptor, and as a result, depolarizes the photoreceptor and makes that photoreceptor continuously release glutamate onto the bipolar cell. But now, in this situation, we now have the all trans form, the straightened out form of retinal. Enzymes are released. Those enzymes remove cyclic GMP. They just break it down. Okay? Now, when that happens, so I'll put in 1. The cyclic GMP is broken down. Now, the ion channels for sodium shut. Yeah, actually, it's something that looks more like that, but anyway, they shut. When this is shut, sodium can no longer enter. Sodium, now bounces off. Oh, but the sodium influx, the flow of sodium, was required to keep this photoreceptor depolarized. Depolarization gone. So now, this cell, no longer depolarized, is going to do something. This neurotransmitter release from the photoreceptor onto the bipolar cell is reduced. And when that is reduced, right, when there is less glutamate being released from the rod or the cone, but again we're sticking to rods for now, onto the bipolar cell, well then those bipolar cells get less input. They're going to provide less of a signal, an output signal, onto the ganglion cells. And as a result, those ganglion cells, they fire at a rate of about 1 action potential per second. Your brain gets a different signal because those ganglion cells are now reducing their firing, their output to the brain. And your brain we'll know what to do with that, but that we get to in a later class. So this is the process, okay? And you really have, it's a very interesting process, because one photon is enough to set this in motion. And because one photon binding to one photopigment can lead to quite a lot of these enzymes being released. Hundreds, if not thousands, of sodium channels get affected, get closed down, and as a result, millions of sodium ions can no longer enter. So in other words, one photon, one quantum of light, right, the amount of energy in one photon, can do all of that. So imagine that you are, as I'm now, in a bright room, right, and how this can completely affects the polarization or the polarity of that cell. This is it, okay? That the cell remains depolarized in darkness because of the cGMP keeping those sodium channels open. That is the dark current. And I don't believe anyone ever uses the term light current, but when light enters, you've now seen what happens. The process is kind of nullified, and that's it. Done. I hope that this, moving through it step by step, made this process a little clearer. It's a vital process in understanding visual sensation. If you have any questions, let me know. See you in class.